reduction, but then I get somebody using it.
Okay, well, it's my great pleasure to introduce my buddy Mike, who knows way more about domain theory than I do, and will be talking about domains and measure theory.
Thank you, Prakash, and thank you to the other organizers for inviting me to participate in the program. It's really marvelous to be here. I've been very much enjoying the lectures so far and look forward to the rest of the week. And again, my apologies for renaming the program, as Val pointed out. It was unintentional. So Prakash asked me to talk about domain theory and measure theory. And I thought what I'd do is give you a brief primer on domain theory at the start, and then try to point to some classical areas in probability theory and measure theory, some of which you saw just an hour ago with Prakash's talk, and point to the links between them and the domain theoretic approach to measure theory. So to start, hello. No, thank you. Now it's on. Okay, to start, the goals of the talk then are to give you a short primer on domain theory, and then talk a little bit about the classical approaches to measures and probability, much of which Prakash covered, but there's some ideas that I think bear mention that he didn't talk about. And then tell you about the domain theoretic approach, and then talk about some applications. And the applications I'll refer to are some recent ones, one of which relates to Dana's stochastic lambda calculus that he talked about on Monday. So what is a domain? Well, it's really a rather simple structure. It's really a partially ordered set with some added properties. But what I'd like to do is emphasize that it's the way you interpret that structure that's important from a computational perspective. In particular, think of the partial order as something that's informatic. So one element's below another if it has less information. So the more information you get, the higher up you are in the order. And a nice example of this that's not really out of the programming language perspective and directly is to think about zero finding. Think about the bisection algorithm. So you have a continuous function that is defined on an interval and it changes sign. How do you go about algorithmically finding a zero for the function? Well, the bisection algorithm says you look at the left half and it changes sign on that, then you choose that. If it doesn't change sign on that half, it has to change sign on the other half, and you use that. And it's deliberately deterministic because you've chosen the left half by priority, but you could do it by the right half first if you wish. But then what you're doing is you're really worrying about the intervals you're looking at and saying one interval is more informative than another if it's smaller than the other interval. So it's this reverse order of containment that's important in this example. And also notice that this order is on the data, not on the function. It's about what the domain of the function is and the data that's being affected. So that's an example of an informatic partial order. And then presumably, if you iterate this process enough times, if you divide the interval, if we use the bisection interval algorithm, you divide it in half some number of times, then eventually you'll get to some interval of length 0, which is a point, and that's the 0 you've been seeking. Of course, you have to have conditions to make sure that's going to work, but in the hypothesis I stated, it would work. The second idea is how do we get to that shrinking family of intervals? What does that mean? Well, it's an expression we call directed completeness. And the notion is based on an idea of a directed set. A directed set in a partial order is a subset, D, that's not empty. And given two elements in it, there's a third one in the set that's above them both. So think of that as talking about consistent information. You have two elements in your partial order, and you'd like to know, are they consistent? Well, if they're in a directed set, then those two have something above them, so there's more information than both of them. And that means that those two together have some consistent information. And directed completeness says, well, if you have a directed family, then in fact in this partial order there's a least upper bound, or a soup as we call it. Okay? So any consistent family of information will have a least upper bound. That's the information all of the elements contain. Now those two things together will give you what are called directed complete partial orders, and indeed that's enough to do a lot of things. People use that, but what we haven't talked about is any kind of computability. We haven't really said what it means to be computable, or something that you have to know in some finite time. And that's what the role of approximation is. So we use this double less than. You could read that as x approximates y. If whenever you have a consistent family of information that contains as much information as y contains, then at some point in that consistent information you already contain what x contains. And that really captures the idea of the x. If you compute enough to get y, at some finite stage you have to have already gotten x. Okay? And that's the notion of, as we're calling it, approximation, but actually computability, if you like, in a finite time, embodied in this theorem. And here, well, I skipped over this part, that for a directed family of intervals, so a filter basis as it's called, the soup is just the intersection. And here, this approximation is the idea if an intersection of a filter basis of non-empty closed intervals gets inside an open set, then one of them is. And so that's how our approximation works. The interval AB approximates CD if CD is in the interior of the interval, because that's an open set. And then CD is the intersection of all of the closed intervals that contain it in its interior, in their interior. Okay, that's this expression of anything, any closed interval. These are bounded intervals in the reals, of course, is the intersection of a filtered family of open intervals whose endpoints are finite that contain it. Okay? So this isn't the usual typical example, but it's one that shows you that domain theory has more to say than just about syntax of programming languages and denotational models. Okay? Any questions on this? So this is what domains are. They're structures that satisfy these three properties. Okay? No? What's going on? Oh. So, okay, so Prakash said he would categorify, if that's a word, what's going on. And I'm going to make some references to category theory, but I promise not to really get into the weeds. But I do want to use the word morphism, or function. And so if we have these partial orders, these domains, what are the proper notion, what's the proper notion of a mapping between them? Well, mappings mathematically ought to preserve the structure. So they're partially ordered sets, so the map F ought to be monotone. And I call them D-continuous for directed continuous because I want to know that if I take a directed subset of P, then F of the sup of D is the sup of F of D. So F preserves this structure of taking the least upper bound of a directed set. So D obviously here is a subset of P. And I'm calling these D-continuous because this is just talking about the order. It's got nothing else mentioned here, although we'll see another version of this in a second. And we could talk about DCPO, the category, apologize for the word, of directed complete partial orders in these D-continuous maps. And one of the main theorems, the fundamental theorem, if you like, of least fixed point semantics is the Tarski-Knaster-Scott theorem. And Fockiant really gave a nice illustration of its use earlier today. But it says if you take a directed complete partial order that has a least element, which we usually denote by perp or bottom, and a monotone self-map, then that monotone self-map has a least fixed point, F. And it's gotten just by iterating the function at bottom. Bottom's below anything, so F of bottom's above bottom, and F's monotone, so when you start iterating, you get an increasing family. And eventually, you're going to run out of ordinals because the set D only has a certain size. And once it starts repeating, then you've reached the least fixed point. Fockiant really used that in his example about data log this afternoon rather. And then the Scott contribution of this was this idea of continuity, that if it preserves do you preserve soups of directed sets, you don't have to iterate forever. In fact, in countably many steps, you will have reached that least fixed point. Okay? And this is the heart of what's called least fixed point semantics. And if you think about unwinding recursions in process algebra, simple unwinding formula is that, say, recx dot p unwinds to p applied to recx dot p for x. And what that's really telling you is the recursive process is a fixed point of the body. And so this is where least fixed points, why you want fixed points, and least fixed points suffice. One comment that Fokyan made was, well, you know, there could be a whole family of fixed points, which one should you pick? In fact, Tarski's theorem, which applies in the lattice setting, says if you take a monotone self-map of a lattice, that means where you have any pair of points have an upper bound and a lower bound, and still directed complete, then in fact, there's a whole family, a whole lattice, sublattice of fixed points for any such map. The least one is gotten by iterating at bottom. The largest one is gotten by iterating at top, and that winds down. And all the other ones are somewhere in between the sublattice that those two bound, but not every point in that, that region from the least fixed point to the greatest one is a fixed point. But that was Tarski's theorem in the lattice case, and Canaster did a topological version of it, and then Dana's contribution was this realization that continuity really told you something about computability.
Mike, if I may make a comment, in the case of data lock that we discussed earlier, in the lecture I focused on finite structures, but actually it makes perfectly good sense on infinite structures. The operator is continuous because existential quantification and the junction distribute.
Right.
And so that's an application that data log closes in omega steps on every structure, finite or infinite.
Okay, fair enough.
So we'll
Nice.
see an example of that in data provenance on Friday.
Okay.
You need to go to the infinite.
Okay, so everybody here knows this stuff, so why are you letting me talk about it? All right.
You don't know what category.
Oh, well, that's another talk. Okay, so properties. Data mentioned this in his talk, that if you take a function from a product of DCPOs to another, that it's jointly D-continuous, as I'm calling it, if and only if it is in each variable separately. That's a very nice result. You know, in real analysis, for example, that is definitely not true. You have to struggle to get joint continuity for a function, even knowing that it's continuous in each variable separately. If you take the set of maps from P to Q, that order them pointwise, that is, f is below g if and only if at each point f of x is below g of x, then in fact, this is another directed complete partial order, and the soup is just gotten by computing pointwise, computing the supremum pointwise. And this is another DCPO. And again, there are Cartesian closed categories of domains. This is not a category of domains because it doesn't have the approximation property. But sitting inside are nice categories of domains. And one we were talking about before the meeting today is bounded complete domains, where every pair of elements has an inf. In fact, every non-empty subset has an inf. And it often happens that you don't need lattice structure. This is quite enough to do everything you want. So I've given this definition in a part with respect to partial orders, but in fact there's a completely topological way to do it. So this is going to bring Prakash's wine glasses into the picture. So he's waking up now. So let's call a subset U of a partial order P Scott open if it's an upper set. And notice, by the way, the arrow is on the left here. So it's the upper set of U is the set of X such that there is a U in U such that U is below X. And Prakash wrote his arrows on the other side, so I'm just pointing out I prefer writing them on the left, as thinking of them as an operator. And the second property is it's Scott open. If I take a directed set whose soup is in U, then the directed set already has to intersect U. So as Peter Johnston said, the Scott open sets are upper sets that are inaccessible by directed soups. Is another way to say it. So this is always a T0 topology. Given 2 points, there's a Scott open set containing one but not the other. It's in fact a little stronger. It's what's called sober. I think that terminology is due to Dowker. But what it really means is that you can retrieve the space from its lattice of open sets or its lattice of closed sets. That's really what sobriety is telling you. If you insist that you have this idea that for any 2 points, there's an open set around either that doesn't contain the other, that's the T1 property familiar to topologists, that implies that your order is flat. Nothing compares with anything else, and so it trivializes. So these are the structures you really want, and domains are sober, although, well, never mind. And then the proper limits topologically are exactly suprema, and they are applied for directed sets. That's the topological view of this structure. And in fact, a mapping between P and Q is D-continuous as I've defined it here, if and only if it's Scott continuous in this sense. So what I'm really telling you is this domain has the property, it encodes this topology directly. You don't need some extrinsic application of it. You can define it internally in the domain. And that's a nice property because it says you can either do it order theoretically or you can do it topologically. We say D is a domain. Well, that means it also has the approximation property. And then the set of points that any element approximates turns out to be a basis for the topology. These are Scott open sets. Why are they Scott open? Well, they're upper sets because of what's called the transitivity relation. If x is below y and y approximates y prime, but y prime is below z, then x already approximates z. And that tells you these sets are upper sets. And it also has what's called the interpolation property. If x approximates z, you can in between approximate z by something that x approximates. And those are exactly the conditions you need to show that each of these sets is Scott open, and then they give you a base for the topology because everything is the soup of the things that approximate it. Okay? All right, so this is all internally encoded in the domain structure. It's nice topological structure you can use. There is another topology I want to talk about, the Lawson topology. These names, by the way, were invented by Karl Heinrich Hoffmann, who is a collaborator in this area, and he liked to name things for people, and so he named the Scott topology for Scott and the Lawson topology for Jimmy Lawson, who's another collaborator, for various reasons. So if you look at the Scott topology, you notice every open set's an upper set. So if you know about Nachman's theory of compact ordered spaces, the open sets consist of open upper sets and open lower sets, and then you get all the open sets as intersections of them. The topology has to be what's called order convex. So what's missing in this definition, if you want a better topology, a finer topology, is you need to know what are the open lower sets. And here I'm alluding to them by saying a basis for the Lawson topology is take the basis you have for the Scott open sets, these set of points that a given point approximates, and then throw out finitely generated upper sets. So F is a finite subset of D. So I'm really saying the open lower sets are complements of finitely generated upper sets. So if you wanted a picture of one, if your domain looks something like this, here's D, then here's a finitely generated upper set that looks kind of jagged like that. So F consists of this point, that point, that point, and that point, and I've thrown them out. And now here I have a point little x, and I look at its way upper set, so it might look like that. So I'm throwing this set out of that, and then I'm getting order convex sets in that way. And it turns out that in a domain, this is always a Hausdorff topology. It's a very nice topology, but it doesn't have all the properties you want for computation, but it's useful in some aspects. And we'll say a domain is coherent if it turns out that the Lawson topology is compact. So then you have a nice compact Hausdorff topology to work with, which is a sort of happy hunting ground for people who really want to prove some nice theorems topologically. All of the Cartesian closed categories of domains have objects that are coherent that are compact in the Lawson topology. So they all sit inside the category of coherent domains and Scott continuous maps. Those are the appropriate ones. But unfortunately, the coherent domains are not Cartesian closed. There's not an internal HOM. So it's the obvious category you'd like to work in, but it just doesn't work. So sorry about that. OK, so what about some examples? Well, one example is the unit interval where you order it in the usual order. And then what about approximation? When is X approximating Y? Well, here, a directed soup, well, it's a chain, so any set's directed, any pair of elements has to compare. And so when you take a soup, you're taking a soup of an increasing sequence. And then you need to know if X is going to approximate Y. Well, if a soup gets above Y, then eventually it has to get above X. Well, that's just saying either X was 0, and there's nothing to really prove, or X is strictly less than Y, because then the soup of a family getting above Y certainly has to eventually get above X. We can take the interval domain. Instead of taking all of the real line under reverse containment, I can simply restrict that to the intervals within the unit interval, and I get the same ideas. You can actually do this kind of an example in topological spaces. Take a locally compact Hausdorff space, like the real line, for example, or Rn if you like, and look at the non-empty compact subsets of X. These are going to play the role of the intervals that we were looking at in the real line, and then say that one of them, A, is below another if B is a subset of A. Again, getting smaller is giving you more information, narrowing down on the information about some property you're looking for. And then A approximates B, again, if B is contained in A interior. And it's the same theorem from topology that tells you this is directed complete, because you know that theorem that says if you have a filter basis of compact non-empty sets whose intersections in an open set, one of them's in the open set. In fact, this generalizes directly to what's called the upper power domain in a domain. You look at the non-empty upper sets that are compact in the Scott topology. Examples, these upper sets of finite sets that I already talked about. If you take any finite subset of D and look at its upper set, that's certainly an upper set by definition, and it's compact because if you cover each of the generators by an open set, you've covered the whole thing, because remember, Scott open sets are upper sets. And because of that, this family of non-empty Scott compact upper sets under reverse conclusion, it's a DCPO, but why? Well, there's a famous theorem by somebody in Hoffman that says if you look at the Scott open filters in the lattice of open sets. So what do I mean by that? The lattice of open sets are the open sets ordered by inclusion. A filter in a lattice is an upper set with the property that any two elements in it have an inf in there. Well, if you take a family of open sets, that's an upper set, that means any open set in there has the property any larger open set's already in there. And the filter property says if you take two open sets in there, the intersection's in there. Then what are the Scott open filters? Those are the ones where if you have an increasing family of open sets and it gets in the filter, the union's in the filter, then one of them's in there. How could I construct such an object? Take a compact set and look at all the neighborhoods of it. Because of compactness, if a union of open sets covers a compact set, finitely many do, but the family's directed, so one of them does, that gets the fact that this is Scott open. And in fact, the theorem says every Scott open filter is accounted for by a Scott compact upper set. That's one of these families. And that correspondence leads directly to the same theorem you use here topologically to say that whenever you have a filter basis of compact non-empty sets whose intersections in an open set, then one of them must be. So that's the theorem you need to say that this is in fact a DCPO, and in fact the domain structure follows as well from that. So that's just there on that tagline. Okay, so this is a nice generalization of a natural idea in topology back to domains that gives you one of the so-called power domains which allow you to model non-determinism. Okay, so any questions? All right. Another point I want to make is about what are called domain environments. So the idea was, if you're going to do some computation on a space, say you have a Pauli space where your computation's taking place, you'd like to embed it nicely in a domain and use the domain structure to do some approximation, some computing. And so the setting for this is what are called maximal point spaces, an idea first studied by Jimmy Lawson, or at least explicated. I think he's the one who defined these spaces. So the idea is to take a metrizable space and look at, as well, accountably based bounded complete domains. So that means there's a countable base for the topology, and it's bounded complete means any pair of elements has a greatest lower bound. And the question is, could I realize X as the set of maximal elements? What's an example of that? Well, think about this case. This case up here where we have the non-empty compact subsets of a space X under reverse inclusion. X appears in there as the maximal elements, the points. And that mapping, sending an element of X to the singleton in here, actually is an embedding topologically from here into the inherited Scott topology on the maximal elements. So that's exactly the kind of setting we're thinking about here. I'd like to know what spaces I could realize in this way. And this is bounded complete because any pair of compact sets, the union's compact, and so that's your inf operation here. There's a theorem due to Jimmy and a trio of authors that says a space M has the property, a space X has the property that there is an M that is a countably based bounded complete domain for which X can be realized as the maximal elements in the inherited Scott topology on the maximal elements, if and only if X is a Polish space. So that says that there's a nice way to build domains to represent them in a setting where you actually can do computation, because these bounded complete domains that have a countable basis are built for that kind of modeling.
Polish space is metric and separable?
That's also true. Yeah, they're Polish. So this is
the definition of Polish.
it's Polish. It's a separable, a topological space that's separable, that has it's completely metrizable. So there's a complete metric that's generating the topology. Okay. Okay. All right. Okay. So those are exactly the spaces you can realize in this way. Okay. Okay. So now okay, so that was my brief, well, if I looked at the NewsHour, my brief but spectacular primer on domain theory. So again, if you have any questions, I'd be glad to try to answer them if I haven't lost you completely in the chalk dust up here or whatever this is, okay? All right, so I'm going to put these slides up, but in fact, I'm going to put up a longer version of them. Prakash convinced me I had enough for 3 lectures, so I reduced it to enough for 2. And we'll see how we do. But anyway, I'll put up the longer list, and there's also a long list of references at the end. So at the least, think of this as pointers to things to look for in the literature about how these things work. Okay, so now what I'd like to do is recall some ideas from measure theory and probability. And Prakash actually gave a nice presentation of what I would call the Kolmogorov view of measure theory. This was in the mid-30s when he came with the ideas of talking about probability spaces using probabilities as set-based functions and measure algebras, sigma algebras, to define them. And he also defined the notion of a real variable at that time. But there was another strand of research that also led to realizing measures and probability measures. And that's largely due to Banach in the early 30s, who had these ideas about Banach spaces. And the key point there was this idea of looking at a metric space, a complete metric space, and looking at the bounded continuous functions from X into the reals, and then taking the Banach space dual, the space of continuous linear functionals, from this space into the reals. And that's the dual space. And the Riesz representation theorem tells you that there's an isomorphism between the measures on X and this family of linear functionals. And the probability measures are the unit sphere in what's called the weak star topology, the topology you get on this from the structure, the Banach space you started with. And the Banach-Aloglu theorem tells you that the unit ball here is weak star compact. And so the unit sphere is as well, and the unit ball is what Prakash was referring to as the sub-probability measures. The unit sphere is the probability measures. But in fact, in this setting, the weak star topology is the same as the weak topology. So a sequence of measures in this converges weakly, probability or sub-probability measures converges weakly to mu if and only if integrating against any bounded continuous function, has the integral of f d mu n converges to the integral of f d mu. Okay? So that's one strand that I wanted to recall. If you don't know this, then this is something to look for. It's part of the functional analytic, if you like, view of how to get your hands on measures. And I want to recall two theorems, neither of which Prakash mentioned. Well, I think he kind of alluded to this one, but not directly, didn't really say it. Certainly, this is one of the basic ideas that simple measures, so these are convex combinations of point masses. Prakash talked about those. He talked about simple functions, but I'm talking about simple measures. So put point mass at a point and take a convex combination of those where the sum of the coefficients here is 1, they're all non-negative, and f is a finite subset of the space x. These turn out to be weak star dense in the probability measures, okay? And if you make this sum less than 1, then you get a family that's weak star dense in the subprobability measures. So that's one of the nice results that comes out of this theory. The other is the Portmanteau theorem that says, here's a collection of ways to think about how measures converge weakly. So it's equivalent that mu n converges to mu weakly, or integrating against any bounded uniformly continuous function, you get the integral of the f d mu n converges to the integral of f d mu. And then these two that I've highlighted in blue are set theoretic conditions. One is that the lim sup of mu n of f is less than or equal to mu of f when f is closed. And dually, this is just by complementation really, lim n of mu n of O is greater than or mu of O, greater than or equal to mu of O if mu is open. Those are two equivalent conditions. And then the last condition is one that's often included, is the limit of the mu n of A is mu of A for any mu continuity set A. And a mu continuity set is just a set A such that the measure mu of its boundary is 0. That's the topological boundary. Okay? So these are all equivalent. They give you nice different ways to think about how convergence works in the weak topology, which is arguably the most important topology on probability or subprobability measures. So I just want to recall those because I'm now going to talk about a domain theoretic view of measures and try to bring in some of these ideas and show you how they're related. So on domains, how do we think about measures? Well, if D is a domain, or just a DCPO in fact, let's let sigma sub D denote its family of Scott open sets. Then we'll say a mapping mu is a continuous valuation on the Scott open sets into the unit interval if it satisfies a strictness property that its measure of the empty set is 0. It satisfies modularity that the measure of the union plus the measure of the intersection is the sum of the measures. It's also the same as the inclusion-exclusion principle, if you like. It's monotone, so that if U is a subset of V, then mu of U is less than or equal to mu of V. And if you have a family, a directed family of open sets, then it's continuous in the sense that mu of the union of the directed family is the sup of mu of the UIs. Okay? So this is the Scott continuity if you view this lattice of open sets ordered by containment. Okay? And this is an idea that arose just in lattice theory, the idea of evaluation. The trick here is to add this Scott continuity, and then you get a connection with measures. And it's easy to see that any Borel subprobability measures induces evaluation here. You just check it out. It's not hard to see that these conditions will be satisfied for subprobability measure. The converse was shown by Jimmy Lawson for the countably based case of bounded complete domains. But Alvarez Mania, Edelot, and Sahib Jarumi proved it for domains in general. So these are really the same thing as subprobability measures. That's what's being said here. You can view them in a domain theoretic way as valuations. So what we do in domain theory is we refer to V of D, the valuations on D, again ordered pointwise. That's this monotonicity condition reflected here. And we want them to be Scott continuous because that's usually what you want with domains. You want Scott continuous maps. And this family sits inside the continuous maps from D, from sigma of D. This should be a sigma of D to 0, 1. It's a sub-DCPO, but the domain structure is, as I'm saying here, very elusive. It's very hard to understand what that domain structure is. Okay? So now what I want to do is I want to try to convince you that this somewhat strange-looking way to represent measures, I guess it's not so strange in light of this observation, but I want to relate it more directly to the classical ways that Prakash talked about and that I just mentioned, and show you that there really is a close connection. So one way is, how do I get this order in a functional analytic way? If you think about the way things were defined a few slides ago, we used integration against functions. That's the Portmanteau theorem, for example, was a way to test things. That was the weak convergence. So if you think about inequalities, it's not hard to show that if you try to say that mu is below nu, if integrating against any function, continuous say, you get less than or equal to, you discover that only time measures, probability measures compare is when they're the same. Okay? So it just degenerates. However, there is this nice theorem that if you take a coherent domain and subprobability measures, then the following are equivalent, that mu is below nu in this pointwise order that I just described, or integrating against a Scott continuous function from D into the reals. So I'm giving the reals the Scott topology. What are the open sets? Well, on the reals, the open sets on R, here's R, like this. An open set is a set from A to the right, and that's the Scott topology on that. It's not directed complete, but that's okay. We can still use it. And I can talk about the maps that are Scott continuous. And I can say that integral of f d mu is less than or equal to the integral of f d nu for any Scott continuous map, and that's equivalent to this condition. Or I'm talking about a coherent domain, so I know in its Lawson topology, it's in fact compact in Hausdorff. And then I could ask, what about this for monotone Lawson continuous maps? Well, one thing to note is the Lawson topology says on the reals, throw out the upper set of a finite set, so you're going to throw this out. Well, now you're going to get an open interval, and so the Lawson topology on the reals is just the usual interval topology. And now you're talking about monotone maps that are continuous from the Lawson topology on D to the usual topology on the reals, and on the non-negative reals, I should say, in both these cases. And then if you have this, that's the same thing as saying this. So this is very much in the spirit of the functional analytic view of how you would generate, say, a partial order. And it gives you the same one we're doing with domain theory. So it legitimately lives in that world. The crucial result that really, well, we thought it really would open up the Pandora's box of what the structure of the subprobability or probability domains are from a domain theoretic standpoint was the work of Claire Jones in her thesis in 1989. I think Prakash mentioned this. But the idea is, how can I compare two simple measures, mu and nu, that are subprobability measures? When do I know mu is below nu? And her answer is that this is true if and only if there are transport numbers. Now, f and g here are finite sets, so there have to be transport numbers indexed by the pairs x, y, and f cross g, so that Rx is in fact the sum of the txy's, the transports. So everything that R has gets shifted to some point in this measure. The sum from over all the x's of the incoming weights from points Rx is less than or equal to the weight on any y. And if txy is positive, then x has to be less than y, or less than or equal to y. So let me draw you a picture which explains why this is a max flow min-cut application. So let's take a point over here and talk about this as the source. Let's take another point over here as the sink. And now what I'll do is I'll put f here. So here's x1, here's x2, here's x sub n, say, where that's the last element in f. And over here I'll list g as y1, y2, yn, or ym. And now what I'll do is I will put arcs from the source to each one of these, and I'll label it with the weight. And so that's Rn. And now I'll put arrows from each of these to the sink, and I'll label these with their weights. And then the idea is, this is a transport problem. I've got these weights coming into these nodes that represent the weights on each of the nodes. I've got these weights going out of these, representing the weights on each of these nodes. They have to get to the sink. What's the maximum flow I can make here? In what way? Well, I can only draw an arc from an x to a y if x is below y. Okay? So I might have x1's below y2, and it might be below yn, and x2's below y1, and it might be below something there, and so on for each of them. And then the transport numbers, the txy's, are exactly the way to fill this in so that you get a maximum flow. And the answer is you can do that exactly if there's a min cut. Okay?
Is the reason for the asymmetry between 1 and 2 that is a sub-probability? You have an equality and an inequality, because you have sub-probability distribution.
Yes. Actually, this should be a less than, okay, for sub-probabilities. Okay? This should be strictly less than, not less than or equal to. Okay? Because on sub-probabilities, you only know that the weights coming in should be less than what you have. Okay? That wasn't your question, though, right?
Well, you've got an equality in 1.
Well, here, yeah, because all of the mass has to leave. All of it has to get moved up. You have to account for all the mass on the lower one. See, mu is the lower one, so all its mass has to go up. Okay?
Not all of it has to arrive.
Well, no, all of it arrives, but it doesn't have to account for all the possible mass above it.
Right.
I mean, you could have, for example, a very simple example, you could take 1/2 point mass at bottom, and you could, if you had a top, you could take point mass at top. And then the half would go up and account for 1/2 of this, but you'd have some left over, right? Okay. And then this same argument, again, this should be a strictly less than here, but in the way below relation, the approximation relation, then you need to say that if txy is greater than 0, then this is strictly less than, and x is way below y. And you do need strict less than to get the approximation that mu approximates nu. Okay? Okay. So again, this is just a transport problem, and max flow min cut characterizes when you can solve it, and so that's where you get these numbers. Okay? All right. So this encodes in a very simple way how this order works on simple measures. And it was thought at the time that this would really unravel all of the strange structure that exists on sub-probabilities in terms of the domain structure in that family. But in fact, yes, whatever you want to do. It really hasn't. As I'll say in a second, it really doesn't. It's given us a lot of information, but not what we really wanted to know. Okay, so one of the theorems I mentioned about probability measures and sub-probability measures was the simple measures are dense. We have the same result here, but I need to define a basis first. So a basis for a domain is a subset, which the property that the set of things that approximate a point in this subset is directed, and the sup of that subfamily is x. So they account for enough approximates for every point. And then you can argue that any domain, if you take a basis for it in this sense, and you take any basis, so for example, the rationals in 0, 1, then forming simple measures over finite subsets of the basis for D and elements Rx in your basis for the interval, this will give you a basis for the sub-probability measures. So you have a nice family of sub-probability measures that any measure can be recognized as the directed sup of a family in there. Okay, and you can even set this up so these things actually do approximate things. So if you know enough about the structure of the simple measures, you know the structure of the space in general. Okay, so this is an analog of that theorem I mentioned in the case of topological spaces, that the simple measures are weak dense. Okay. So now there's a series of papers by Abbas et al. In which he tried to exploit these ideas, and I want to mention some connections that arise that really reflect these ideas in the portmanteau theorem. You remember that was the theorem that said here are equivalent conditions for weak convergence, and one of them was exactly this kind of a condition on all open sets, but we're talking about Scott open sets. So what he showed was if you have a countably based domain and a sequence of measures that are subprobability measures, then it's equivalent that in this domain, this is a domain now, I can talk about its Scott topology, the mu n's converge to mu, then the lim of mu n of any Scott open set is greater than or equal to mu of mu. That's exactly the same condition in the portmanteau theorem, except we're restricting to Scott open sets. And a corollary of this is that if you take a separable metric space and an embedding as the maximal elements of this D, so that it's a G delta, then that lifts to an embedding of the probability measures on X into the maximal elements in the subprobability measures with respect to the weak topology. So that says that this is the point of the saying Scott is weak on the top, was the idea that you embed these in probability measures as the maximal elements, the top elements in this space, and they inherit from the Scott topology exactly the weak topology from measure theory. That result actually was generalized a bit in some work I did with Frank van Bruegel, Joel Wachnien, and Ben Worrell, in which we accounted for the other half in the case of a countably based coherent domain. Namely, you see the two conditions now, not just the lim inf of mu n of a Scott open set U is greater than or equal to mu of U, but also the lim sup of this type of a closed set, the upper set of a finite set, that should be a mu n, sorry, is less than or equal to mu of the upper set of F. So here are the two conditions that the portmanteau theorem says, and actually, just from this result, you can then show that if D is coherent, so is the set of subprobability measures, the domain of subprobability measures in the Lawson topology, because it agrees with the weak topology, and that's just the portmanteau theorem, because the portmanteau theorem says in the weak topology this space is compact, in the Lawson topology is Hausdorff, and the map is 1-to-1, so it's a homeomorphism. Okay, so again, what I was doing here was just trying to tell you that the conditions in one of the fundamental results, the portmanteau theorem, do appear in domain theory and give you some nice results. Sorry. Okay, so I've been alluding to this mysterious structure on the subprobability measures. Again, a little more category theory. It extends to an endofunctor that is a monad. You just push a measure forward. Given a map from P to Q, you just take a measure on P and push it to Q by this formula, which is the same one that Prakash used. I'll generally denote this by F so lower star of nu. So that means push the measure nu on P forward to mu by saying F star nu of a measurable set is nu of F inverse of that set. So here's almost everything we know about the domain structure of this functor V. It takes coherent domains to coherent domains. I just showed you a proof of that. If you take a rooted tree, so a binary tree, say, infinite, then the subprobability measures on that is a bounded complete domain. That's nice. If you take a finite tree that's upside down, turn it upside down, but finite, then that's in another subcategory that's Cartesian closed. That's it. That's the only structure we know, domain theoretically. So it's kind of disappointing. This structure was meant to model probabilistic choice, P plus sub R Q, which is a process that's supposed to fuse P with probability R and Q with probability 1 minus R. The problem with it doesn't play nice with other structures. We don't know of any Cartesian closed category of domains that's invariant under this. it doesn't satisfy a distributive law. So this is some category speak to say that if you try to combine probabilistic choice and non-determinism, and I do differentiate the two, then you don't have a nice way to say what you're going to get. There is a result that's out there that talks about some laws you generate, but they aren't orthogonal. You'd like them to be orthogonal. You'd like to say probabilistic choice is really different than non-deterministic choice, and you could think of them separately and they don't interfere. We have no models to reflect that. So that actually led to the idea of doing random variables, and I want to spend the last part of this talk, last 10 minutes as it were, talking a little bit about that. This is some very recent results, and it will get to Dana's ideas, but in a much more general way. So Prakash talked about A infinity for an alphabet A. This was the set of finite and infinite words over A in the prefix order. The simplest example, well, not the simplest, you could take a one-letter alphabet and it's really simple. But if you want an interesting alphabet, in fact, one that seems to have a lot of computational weight to it, is take the finite and infinite words with zeros and ones in them, bit words, and order them by prefix. So then you get this nice rooted tree. The empty words at the bottom, the first level is heads or tails, 0, 1. The next level is outcomes of 2 flips of a coin. The next one as 3, and so on as you work your way up the chain. So if you let, there's an infinity missing here. These slides are really a mess. If you let the infinite words, you think of them as the Cantor set, the usual middle third Cantor set sitting at the top. The topology you usually give to the Cantor set is the inherited Scott topology. So if you take these wine glasses that Prakash talked about, that's the upper set of a point that's finite. That's a Scott open set, and only for finite sets. And what it intersects with in the Cantor set is an interval, and that's the way you get the nice interval on the topology on the Cantor set of infinite words. But you can look at any level, the set of m-bit words, and think of those as the outcomes of m flips of a coin. And if you're thinking of modeling a computation that's doing this, then that's the frontier at which computations are doing things. You're flipping coins for some number of times. One of those outcomes occurs. Then a random variable will take that outcome and give you a semantic value for it. That's the intuition of what's going on here. An interesting point about this structure is that you can collapse the whole Cantor tree, all the finite and infinite words, onto the set of words of length at most m. This tree structure says if you want to take a word up here and send it down, what do? Well, it's a tree, so there's a unique path to the root. So there's a unique path, there's a unique point with exactly m words on it that's below this point, and every point has that property. That's the retraction. And these maps, you can actually say are continuous in the Scott topology. This is a nice closed set in the Scott topology. And between any two of these, if m is less than n, then there's a projection from the n-bit words to the m-bit words. And it's doing what you think. It just truncates the word to the first m bits. Okay? So that's all very nice and intuitive. So what a student of mine did was he talked about looking at this as a model of computation. So talk about the what are called full antichains. The set of m-bit words are an antichain. No two of them compare. Think of that as prototypical. It's also a closed set. It's finite, and so it's closed in the Lawson topology. And it's full because every word in the Cantor set has an m-bit word prefix. So its upper set contains all of the Cantor set. And he ordered these, so the fullness is just the Cantor sets contained in the upper set. And he ordered two of these by saying m is below n. If m is below n in the Egli-Milnor order, which means everything in m is below something in n, and everything in n is above something in m. Or, said another way, there is a projection map that takes n onto m. So every word here has a prefix in m, and every word in m has an extension in n. That's the order you want. And then he called this family his family of random choice possibilities. And the idea here is you take one of these antichains of possible outcomes of some number of flips of coins, and then a mapping that maps that set of possible outcomes to the domain D, that's your semantic domain. And what it represents is the choice you're going to make. If you get a particular outcome in M as the outcome of the flips of coins, then X will tell you what value to take in D to associate to it. And again, order these by this order on the antichain part, and assume as well that this mapping X on the smaller antichain, when you project the n-bit words down to M and then followed by X, you get something less than or equal to Y. And he showed this is a monad. It's a monad on the bounded complete domain, so it's very nice computationally. And it enjoys a distributive law, so it behaves nicely with respect to non-determinism, with at least the upper power domain. Now, Dana's model on Monday, he talked about P of n, the power set of the natural numbers, as a model for computation. And all of his work was done in that model. That was his whole universe. And his randomness was a random variable from the unit interval to P of n. So Tyler's monad generalizes it. Here's the syntax of a language that's called randomized PCF. For those of you who know, PCF is the simply typed lambda calculus over ground types of naturals and bools and function types. And then here's all the syntax that you have: true, false, zero, successor, predecessor, testing for zero, if then else, variables, lambda abstraction, application, recursion. And then this is randomized choice. And that he and Tyler instantiates using this monad. That's how he achieves a model for, in fact, this structure. His construction actually allows you to model randomized algorithms. It's interesting because it feeds the outcome of the random tosses to both a process. So for example, if X is testing a prime P, whether a number P, whether it's prime, and Y is testing, say, some other prime Q, and you want to know whether P or Q is prime, then you feed the same random choices to X and Y to test whether P or Q is prime. And he implemented this, and in fact there's an implementation on GitHub, and it works. It's really nice. It gives you a nice model. And this is what Dana was really hinting at, the idea that this stochastic lambda calculus could give you some way to model randomized algorithms in this domain theoretic approach. Okay, so the last thing I want to talk about is some more recent work. Domain environments were ways to embed topological spaces into particularly nice domains as a set of maximal elements, and then seek to approximate Scott maps between X and Y with Scott continuous maps that approximate them between the model for X and the model for Y. And some work I've been doing recently has been looking at this in a way to approximate measurable maps, the maps that Prakash was talking about. And for that, I need to say a little bit more, but a stochastic process is just a family, people like to say a time-indexed family of random variables, where each random variable is from the same probability space into S, where S is a Pauli space. So I mentioned that before. And there's a remarkable theorem that I've been just intrigued by for some time called Skorohod's theorem. And it's fairly easy to explain. It says if you take any Pauli space, these are the spaces that probabilists look at as possible places for random variables to take their values, and you take any probability measure on it, then if you let lambda denote Lebesgue measure on 0, 1, there is a measurable map from the unit interval with the Borel sigma algebra as a measure space to S, so that the push forward of Lebesgue measure is the measure you started with. It's kind of amazing. It says no matter what measure you start with, this is for probability measures, on any Pauli space, you can account for it just by knowing Lebesgue measure and a measurable map. Moreover, if you take a sequence of measures on S and a measure nu such that this sequence converges weakly to nu, then the random variables that you chose have the property that the push forward of lambda under X was nu and the xn push forward of lambda was nu n, then these xn's will converge to X almost everywhere with respect to lambda. So this is not only telling you you can get each one with the push forward of the map, but in fact, the random variables you choose have to converge almost everywhere. So this reduces convergence in the weak topology on this abstract measure space, of this S here, to convergence of measurable maps almost everywhere. Okay? And what I've managed to do recently is to prove this theorem using some of the structure, this Cantor tree and all. It's a little late, so I'm not going to go through this. But the interesting point is you have to construct, you do it by approximating the measures nu n and nu n plus 1. You approximate nu with these measures. And you find simple measures that do this approximation. And you construct functions with the properties you want just for each of these simple measures. And then the thing that you need to make sure that you get an increasing sequence here is exactly the transport numbers that I talked about from the splitting lemma of Jones. So it's very nice. It says you can get any measurable map in this way. And in fact, the corollary to the proof is if you take and embed a Polish space in a nice domain environment, and you take any measurable map from the interval to S, then in fact you can say F is almost everywhere equal to a G, where G in fact is the soup of what I call piecewise constant maps, these maps that I constructed using the splitting lemma. Okay, that's enough. I've got like 3 slides of references that'll get put up, plus a more elaborate version of these slides. So let me stop here. Thank you. Any questions? Yes, Samson.
So does this result say something about the constructive content of Scorahot? I mean, is it to give you a constructive version?
To the extent that the way you can get these mappings is constructive, yes. You'd be able to say that. So if you had enumerated a basis, in particular in the context of this corollary here, if this MS was done in a way where you could enumerate the basis, then you would be approximating simple measures there, and you could conceivably constructively do things. Okay. I hadn't worked through that, no, but I can't see why.
It could be the basis.
Yeah. I'm not claiming it's true. I'm saying that, yeah, if you enumerated this structure, a basis for this structure, then you should, in principle, be able to do it. But there might be a big.
Was the original proof? Was it completely?
No, the Scorahot, well, there are lots of proofs of this. In fact, they're generalizations. And they're like point set topology, if you ever looked at that, where you pick points, but you're in measure theory world, so you don't have to worry about open sets so much. You just need measurable sets. And so you can throw things away, and you do it sort of in a nice way. But it's no pun, random how you choose the points. Okay? So in a sense, what this is doing is say there is a sort of algorithmic way, in a sense, to generate this from the structure you're looking at. Yeah?
I have another question about the semantics for the
RC?
language.
Yeah.
So Dana put some emphasis on this. He was using this
Coins in your pocket? Yeah.
To ensure, so that you had to kind of have the stream of random choices, and you weren't sort of reusing the.
Yeah.
That was needed, I think, to get some referential transparency. Probably, I'm just wondering what's happening here. If similar's happening, or something.
No, I don't think I don't think Tyler used a continuation style semantics. He used sort of a standard semantics for this, and then just augmented it by feeding the same stream. He didn't split the stream that way that Dana was doing it by saying, well, you get this one.
So does that mean you could have order-dependent effects?
That I don't know.
Right. I mean, I think any of these semantics were definitely better. I mean, I think Prakash made this point after Dana's talk. There should be some comparison with an operational.
Right. He does have a denotational and operational semantics for this. Yeah. Actually, that was a question I was asking Prakash over lunch. Was this idea of splitting a stream of random choices by giving the evens to one process, and then of the rest you give the evens to the next, and so on. And are those really random? And I don't know the answer to that, so if anybody does, I'd be interested to know. Yeah?
There is a universal Polish space, this horizon space. Is there something like it for these domains? I mean,
Sorry?
there is a universal Polish space, right? Horizon space.
Yeah. Well, I mean, Dana's domain, P of n, is a universal domain. So for countably based bounded complete domains, yeah. I mean, he mentioned that. So you might ask, why do all this structure? Well, there's some things I didn't mention here, but what you'd like to do is you'd like to have domains particularly tailored to a given syntax you might be looking at, and that's really tied up in solving what are called domain equations, getting domains that satisfy certain combinations of the constructs we can use. I haven't mentioned a lot of them. And that gets us back over to Sampson's domains in logical form, where you can tightly tie a logic for a domain to the way you constructed it, things like that. But this all gets into the weeds of category theory and how you go about doing that. But those things I haven't talked about, that's heavily dependent on stone duality, which enters very prominently in there. So there are a lot of ingredients that I left out here. So I actually I thought I'd write a slide of things I left out, but it got to be too long. So
you left it out.
So I left it out. Okay. Any other question?
Mike again.